Okay, so the plan for today, I think two items. One is continuing what we talked about last time about how to derive posterior, conjugate posterior for the normal case. And the remaining time will be used for doing lab 2. Okay. All right, so last time, let me share my screen. We did a detailed derivation of the case where the mean is unknown in the normal model. And then we looked at how you can do it. So this is the results that we saw last time. And in class, we did a step-by-step of how to derive this posterior for mu. And the specific situation here is that we assume the standard deviation is known in this case. So mu is the only unknown parameter. And that left us the skills and I guess the flexibility of treating everything related to sigma to be a constant. And of course, in the end, we were using phi, which is the precision, which is 1 over variance to facilitate the derivation. But you can always, like, if you want, you can keep it as sigma squared and then do the rest, that's fine. But the reason, as you can see, what we're doing here in equation 14 is if we are able to put it in terms of the precision, then it's easier for us to actually read how the posterior normal mean is the weighted average of the prior mean and the sample. Okay, you can do it in sigma square, that's totally fine. But it's something useful to think about. And one more thing about this posterior is last time I think we didn't get a chance to talk about the variance. Here is the standard deviation. So keep in mind that, so let's see. So standard deviation is square root of 1 over phi 0 plus n phi. So that means the precision, which let's use phi n, is phi 0 plus n phi. Right? So precision, again, is 1 over variance. So you just do the reciprocal and then you get it. And as you can see here, you can see that the posterior precision is the sum of the prior precision and the data precision. Both of them are normally distributed, so they represent the same thing. I mean, they're representing 1 over the variance in the model. Okay, one is for the prior, the other one is for the data model. Both of them are normal. So this sigma 0 connects to phi 0, and then this phi connects to this, this sigma connects to this. Okay. Yeah, so precision, so let's take a break and think about this. So what does precision mean? It's 1 over variance, right? So variance is talking about the variability. The larger the variance, the larger the variability, okay? Precision is the reciprocal, so what does it mean? The smaller the precision, the larger the variance, right? So now if you look at the posterior precision to be the sum of 2, so that means, so first of all, phi 0 and phi, they're both positive, right? So that means phi n is going to be larger than either of them, right? So that means, let's say, variance of the posterior is going to be larger than either, going to be smaller than either of this, right? Let me say it again. So if you look at equation 14, what I wrote on top of it about the precision, so we see that the posterior precision is the sum of the prior precision and the data precision. And both the prior precision and the data precision should be positive, so that makes phi n larger than either of them, okay? Because they're positive. So the reciprocal of that, which will be the variance, that means 1 over phi n going to be smaller than either of them, okay? And variance being smaller, meaning that it's going to be smaller spread, meaning lower uncertainty, right? So that's not surprising. I think we actually saw it in the plot. I didn't plot them together, sorry. But if you plot the prior distribution from U and the posterior distribution from U together, you're going to see again what we saw for the beta binomial case, that the spread of the posterior are going to be smaller. Okay? So that again reinforces the idea that when you start with the prior, you have higher uncertainty, especially if you're going to give a really flat prior. you don't know exactly where the parameter should be, so you're just going to give it like a wide prior to let the data dominate. And then together with the data, it helps us to sharpen our belief by shrinking the spread of the posterior. Okay, so that will be another feature you will see if you do the plotting. But as you can see from the particular normal conjugate prior that we do over here, that yes, this also reinforces our understanding. We can see it mathematically how the posterior precision is larger than the other two, and then that means the posterior variance is going to be smaller than the other two, and then that in the end tells us how data is sharpening our belief. Okay, so again, in those simpler cases, it's easier to see. Later on in the semester, we're going to see more complicated situations, so it won't be as clear as what we see now. But I'm hoping that through those simple models that we're introducing at the moment, that you'll be able to see the particular features of Bayesian inference. Okay, and this is, I mean, the recurring theme that you're going to see throughout the semester. Cool. So this is to wrap up, or like I guess recap what we did last time. And for the lecture today, the remaining, I mean, the first part that I want to talk about is, well, last time I said instead of fixing sigma, you can also fix in mu. Yeah, you can also fix mu. So let's just look at this for a little bit. Like, this is usually not the focus of inference. People care more about the mean. But I do want to show you that, well, if you have a 2-parameter model for the normal sampling model, and if you fix one, the other one, actually, we know some other, like say in this case, if mu is known, sigma is unknown, there is also conjugate prior for this, which later on, you're going to see how useful it is when we put both this unknown. Okay. So I'm going to introduce a new distribution called gamma this time. We won't go into the detail of how gamma behaves, but I want to take the chance to show you how to do the derivation, and then get you more familiar with how posterior is being derived. Okay. All right, so this is the case that mu is known, sigma is unknown. Okay, so suppose we know what the mean is, and I want to make inference about sigma. So the, okay, typo, so here should be sigma. Sorry, I will update this later. And so there's only one parameter in this model, which is sigma. So if you want to do it, remember, so the sampling model doesn't change. It's still the normal model, okay, the IID. And then the joint likelihood, now because only sigma is unknown, we're going to treat mu as constant. So the likelihood function is only in terms of the unknown parameter, which becomes L sigma. Okay? And for the prior, we do something very similar to before. We put whatever is known in the condition just to remind us that we assume that we know it. Okay. So this is what we have in the conditional. After the conditional sign, mu is highlighted in red and taken as known. And then ultimately, we're going to try to derive what the posterior for sigma is. And then here is sigma given all of the data and the other known parameters. Okay, so same procedure, except now we focus on sigma instead of mu. All right, so the new distribution I'm introducing today is called gamma. I will give you the density in a minute. But for now, let's say, so typically, a conjugate prior that people can use for sigma is not directed for sigma itself. It's for the precision, which is 1 over sigma. Okay, so now you see again why people like to work with precision. It's just more nicely like done. So the typical posterior, I should say, the typical conjugate prior that people put for 1 over sigma is this gamma distribution. So I'm going to give you the density in a minute. But gamma distribution has 2 parameters, alpha and beta. Okay. And the data sampling density will still be the same. Okay. So now, as you can see, the goal is go to the next step, is how to derive the posterior. Okay, so I'm showing you the results for now. This derivation is much simpler than what we did previously for the mean case. But I want to show you that if you start with the gamma alpha beta for 1 over sigma squared, and then if the sampling density is still the IID normal that we used to have, then the posterior distribution for 1 over sigma squared is going to be another gamma. Okay. The other gamma, I mean, the details, we're going to look at it in a minute. But this, as you can see, shows that gamma is a conjugate prior for the precision if your sampling model isn't normal. Okay, so you start with gamma, alpha, beta, and then you get to another gamma, which is a little bit more complicated, obviously. We're going to see how you can do it. And then we're going to go to the lab. Okay. So one last thing is, yeah, I should also say gamma is a pretty widely used function. I mean, gamma is a pretty widely used distribution. So in order to do any kind of posterior summary, you can use the R gamma function in R. And then again, all of those values here, like alpha and beta from the prior, so you know their values, right? And you know the sample size, like this. Again, we saw this before. You can compute it from the data, and then you're able to get all of this to do the posterior summary for 1 over sigma squared. Okay. And as a demo, again, you can recalculate about the code later, but this is the detail of, say, if I start with that gamma 1, 1 for my 1 over sigma squared, then similarly, I can compute what is my alpha n and beta n. So these are following the formula that I showed you before. You get the posterior parameters, the mu alpha and mu beta. And then you're able to say, like, using R gamma to generate a large number of draws and then summarize them. Okay, but of course in R you also have D gamma, P gamma, and Q gamma. Yeah, you can use those to do the summary as well. So the core of the story is that we also know exactly what the posterior distribution is. It's a gamma distribution. Okay, and once you know that, any kind of summary can be done through simulation or through this exact solution based on various gamma functions available in R. Okay, all right. So what I want to do now is just to show you, say, more like an exercise. So for you to get more familiar with recognizing what is the posterior distribution, especially like collecting the right terms, recognizing what is constant, what is not, and then in the end, of course, recognize what the posterior distribution is. Okay, so let me show you the gamma density. So the prior is 1 over sigma squared. Okay, we work with the precision. Even mu is gamma, alpha, and beta. Okay, so the density, I should give it to you now. So the prior, the density is beta, so that's the second parameter raised to power of alpha, and then it's gamma function alpha, 1 over sigma squared, which is the unknown parameter, raised to power of alpha minus 1. And then lastly, so I should say, oh yeah, let's just use it. So you see that I try to use parentheses over the unknown parameter. Okay, so these are the density. Okay. And the likelihood, we know that, is the joint IID. And remember, we now use L. I mean, we still use L stands for likelihood. And instead of sigma, I'm writing in terms of 1 over sigma squared because I'm treating this as the unknown parameter. Okay? So the likelihood, remember, this is not new now because the likelihood is from the joint density of the normal, right? So what we care about, obviously, so I will write the overall expression for you again. So this is 1 over sigma, right? And yi minus mu, take the square and then the thing. Okay, so this is from the normal density. Okay? So I will do this step for you, and then I will let you try to derive the posterior. So again, recognize what is constant. So here, this whole thing raised to the power of n, right? And then in order to express, so notice that we're trying to express everything in terms of 1 over sigma squared. So now this 1 over sigma, and then its m producting together will become 1 over sigma squared to the power of n over 2. Yeah, so it's 1 over sigma, the whole thing raised to power n, which will be 1 over sigma squared, the whole thing raised to power n over 2. Okay. And lastly, we're trying to, again, express what is in the exponent function. So that becomes, remember we're doing a sum. So it's going to be, let's see, say 1 over sigma squared. I put parentheses around it just to make sure that we know this is the unknown parameter. I remember because we were producting all of the exponents, so inside the exponent is going to be the sum. It's I from 1 to n, and then yi minus mu squared. Okay? Yeah, so just to keep our old practice, recognize what is constant, what is not. Okay? So in terms of 1 over sigma squared, which is the parameter of interest at the moment, the 3 terms, any of these are constant? Which one? Or which one? The first one is constant, right? So later you see that you don't need it. That's good. However, the other 2 both involve 1 over sigma squared. Okay, so you're going to keep this. Okay. All right. So I'm going to write the beginning for the posterior and then let you try out the work. Okay. The posterior is 1 over sigma given all of the data point and given mu should be proportional to its prior and the likelihood. Okay. So I start writing the proportional sign for you so you can start throwing out those constants. And I should also mention that in the prior, there are 3 terms as well, right? And just like in the likelihood, the first term is a constant. So that you don't have to worry about it. So that means to derive the posterior, you focus on the second 2 terms in the prior and the second 2 terms in the likelihood. Okay. So I'm going to pause for a few minutes so you can derive the posterior. And this one, like I said, is simpler than a normal case because there you have to arrange all of these terms and then in the end you have to complete the square. Here is more about recognizing what's outside the exponent and what's inside of it, and then you're able to recognize the posterior gamma for it. Okay? So take your time, and I will walk around to help. So if you're able to see eventually a term that is 1 over sigma squared raised to some power, and the other term is in the exponent of negative 1 over sigma squared multiplied with something, then those 2 will actually tell you what the posterior gamma distribution should be. Okay? So on the top, as you can see in the prior, I sort of wrote out the generic gamma distribution. You see, it's a normalizing constant in front, which we don't have to worry too much about. But it's going to be 1 over sigma squared, which is the unknown parameter raised to something. And then it's in the exponent, it's negative something multiplied with the unknown parameter. So those are the terms of a gamma distribution. So in the posterior, when you're able to derive and come to the product of 2 terms in that fashion, you're able to recognize what the posterior gamma is. Okay? So I will start doing it on the board. You can check. And you can, of course, talk to your neighbors in the meantime. So are you able to get the same results? Yeah, so this one, like I said, is simpler. And it's actually a practice of just keeping like -1, the sign over here. We did the same for the beta binomial previously, right? Like we never really compute that -1 because we know eventually, in order to recognize it as a beta density, we will have to recognize some parameter, like the parameter raised to power of something -1. And then 1 minus p raised to something, the power that is something -1. So here, similarly, as you can see generically, if it's gamma, alpha, and beta, that's how those alpha, beta parameters come into play. So that's why we recognize this as the first parameter, okay, and this as the second parameter. Okay. Yeah. So that's why I said earlier, here, this term, we don't have to worry about it because yi is known and mu is known. Okay, you don't have to expand and then do the sum. That's totally okay. However, previously on Thursday, we needed to expand it because we're trying to derive the posterior from mu. Okay, and that's why like there's mu squared, and not only mu squared in the likelihood, but also mu squared in the prior, and then all of that add up together. Okay. But essential skills to have in this course is that you have to know how to derive posterior. If I give some like prior distribution for you, the likelihood for you, like the key, as you can see, is recognize what is the unknown, what is known. Whatever is known, you can sort of like don't worry too much about it, right? And then in the end, of course, you have to grab the right terms and then get the right expression. And then in the end, you should be able to recognize what the posterior distribution is if it is a conjugate, okay? Later in the course, if it's not conjugate, well, yeah, we won't be able to do it, but we have other like tools to do it, but this are the building blocks. Okay. Cool, so I think we're good on this. And again, like I said, I have a 2-page note for the derivation we did today and on Tuesday, so I'm gonna post this to Moodle afterwards for you to check the details if you couldn't get them through class. But of course, if you have extra time, you can watch the video that we posted on YouTube anyway. That's just the recording of the lecture. Okay. All right, so so this is pretty much what we did, and then again, let me just bring back this slide again. So we did the derivation, and we saw that earlier. That if you know what the prior distribution is, you know exactly what the posterior will be. It's a gamma with those 2 parameters. So those again is from the data. Okay, remember it's alpha plus n over 2, so we have that. And then for the beta n, which is beta plus 1 over the sum of the squares, so I'm using it over here. So you can just do it. And lastly, now you know this alpha n and beta n, use R gamma, and then just input the shape and the rate. So these are the name of the 2 parameters. You just input them, and then you can draw like a posterior summary of this. Okay. So this is doing summary through simulation. You can also do summary through exact solution, okay? And we can do it because we know it's a gamma distribution. Okay? And for the normal case, we can do it because we know it's a normal posterior distribution. Okay? So I think this, maybe I just should mention one more thing before I go to the lab, because yesterday during office hours, some of you were asking about for the, I think it's the lab, yeah, I think it's the lab question. about say, well, when we're doing beta binomial, I should say, when we're doing the inference for proportion, before we introduce beta binomial, we did introduce the discrete prior that you can use for the unknown p, right? Like we set up as at 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and then we assign like a list of probabilities that sum up to 1, and blah, blah, blah. And then what we did back then for doing the inference is we're using, say, in the teach-based package, we're using like the Bayesian crank, and then we create this Bayes table and then do a step-by-step, right? So that works if you're using the discrete prior, because essentially that Bayesian crank and the Bayes table, what it did for us is implementing Bayes rule, right? We're like evaluating like the probability, like the prior probability at each p, the value of p, and then we evaluate the d by norm at each p, right? And then we multiply them together, it's a joint, and then in the denominator, it's the sum of all of the joint. And then we're using Bayes theorem to do that. However, once we start talking about conjugate, so previously it's about beta binomial, now it's about normal for the mean. And of course, what we did just now is a gamma normal for the precision. When we're doing conjugate, we know exactly what the posterior distribution is, okay? So I would recommend you to stay away using like Bayesian crank anymore, because now we know exactly the distribution. You can do either through simulation, like R gamma, and also R norm, and also R beta, when you're like, depending on which parameter you're working with, to do like inference through simulation. Or you can use other functions like D gamma, P gamma, and Q gamma, that kind of stuff. Depends on the task, like interval, like credible interval, or hypothesis testing, et cetera, et cetera. So it depends on what you need to do. And the reason is, again, because we know exactly what the posterior distribution is. So it's much easier actually to do it in the way that I just said. However, previously, when we're working with discrete prior for the unknown proportion, we don't know what the distribution is, but we know Bayes rule. So we can use Bayes rule. And it's not too difficult to do because you don't have that many options. I mean, for the p value, like the values of p, you don't really have that many. But of course, once you're using like R, like if you have 100, you can do it anyway. But the key point is, back then we don't know what the distribution is, but we can approximate it, okay? Now, we do know, and as we discussed before, the continuous beta prior is much more flexible than the discrete prior that we put before. So I hope you can start to grab the idea that this is like, once you know what the posterior distribution is, we don't have to rely on Bayes rule anymore. However, keep in mind, whatever we're doing earlier, all of this, when we're doing derivation, what the posterior distribution is, we still rely on Bayes rule. They just hidden in the derivation step, okay? But once we rely on those and get to the posterior exact distribution, we don't have to worry about it anymore. We can just use simulation or exact solution to do inference. Okay, yeah, so this came out yesterday like a couple of times, like I couldn't get the numbers right. So I was a little confused as well, but I want to get the chance to talk to the whole class about this idea. Okay, cool. So that's pretty much what I want to talk about in lecture time. And the remaining time for today is for Bayesian inference for unknown mean. It's a lab work. I post a lab instruction on Moodle, so if you bring your laptop, and then so pretty much I'm asking you to do 4 different tasks. Okay, Bayesian hypothesis testing for the mean, Bayesian credible interval for the mean, prediction, which means that we're trying to make a new predicted value, which is the log total expenditure from last quarter. And then lastly, it's the posterior predictive checking. So in the document, so maybe now let me stop this.